Today, we are going to talk about the diode, actually the diode, when it is illuminated. When the diode is illuminated, it is no longer have characteristic IV curve, something like this. This is only for PN junction without being illuminated, without illumination. So under illumination, the curve will change, but it's not change in very significant. Actually, it's just offset, doing the offset of curve. So it's very easy. Okay, so let me just refresh you the curve. The curve, when forward biased, it is no resistance, hardly any resistance. It's conducting. When you do the reverse bias, it is hardly conducting. However, if you reverse bias past the breakdown voltage, then it will break down. Then the current increase very fast. As you know, the breakdown may be harmful to PN junction because it has very high voltage while it has very high current. So the power generated by breakdown is very large. The power is V times I. So it's very large. So it will convert the power into heat. So it may burn the PN junction. So we don't want to operate the PN junction under the breakdown condition, unless the breakdown is carefully controlled, saying that you need to series connect the resistor so that the current will never be higher than a certain level. Then you can use breakdown. Otherwise, be careful. When you are using breakdown, sometimes it will have a disastrous result.
So what type of application can use this?
The breakdown. Just similar to this one, because usually we use this one as a DC AC converter, right? Yes. And for this one, we use the breakdown voltage to control the voltage of the output. So there are some applications, but be careful. If you are not using series resistance to connect with that, then this breakdown, the current will increases, then burn the PN junction. Okay. Okay, so we are going to proceed with now photodiode. Photodiode means we can use a diode, and that is specifically designed for absorbing the light and generate electricity. Okay, or I'll mention about that. Photodiode is not limited to solar cells. It can be in application of photodetector. Okay, so please take out the handout that you received yesterday. I modified it a little bit, so the sequence might be a little bit different, but that is not should not possess very big problems. Just take a look and you will see the results. You will have all the stuffs because, for example, this one, you already have this one yesterday, right? Okay, we have, since for photodiode, we are not operating at very big reverse bias, so we are only concerned about the voltage near zero voltage. And this is the equation for the diode. Now, when the PN junction is biased, reverse biased, so you know this is the Venn diagram for reverse biased PN junction, right? Yeah. So they will not have diffusion current, but they have drift current. Drift current means the particle just drift into the transition region and being passed by to the other side. So it's controlled by drift, it's not controlled by diffusion. Okay, so electron will go to the n side, from p side to n side. So going right, and hole will going left. Okay, hole will going left. And since they are minority carriers, they are not the majority carrier in a respective type of semiconductor. So the amount will be very low, hardly any. So the drift current is very low, hardly any conduction in the reverse bias condition. Okay, make sure, be careful about the direction, because what I'm going to tell later on, I will ask you the question about what is the photoelectron, the flow direction of photoelectron. Will that be the same as drift current, or will that be the same as diffusion current? It's very important in equating, in deriving our equation. So for drift current, the electron going from left to right, hole from right to left, all right? Now, this is the condition when PN junction is illuminated, but not biased. Okay, so now the left-hand side is P junction, N-type is N, right-hand side is N, all right? So you are illuminated by the light. I use yellow stuff. You may not be able to see very clearly. Okay. Still, we have depletion width. All right. But other than depletion width, we have an extended distance, so-called electron diffusion length and hole diffusion length. So even though we are not biased, you know, they still have a very small field. Even though we say there's no field, right? Hardly any no field, but actually there's still field because we biased it. No, so we are not biasing it, but there's still a little bit field that going to this side. That will cause the electron to flow to the right and holes to the left. Because, you know, this is a simplified model saying that all the field is crossing a very short distance near the interface, but actually it is the simplified model. There's still very small field in this flat region. Okay? Now, why we need to consider this distance is because if electron inside this region, they will still be able to feel the field. So go to the right-hand side and hole go to the left-hand side. However, they might recombine with at the defect and disappear or disappeared during their transfer to the interface. So there's a parameter called diffusion length. Diffusion length means the average length it got collided and disappeared for the particle in the movement, during the movement in the semiconductor. Okay, so this is a material property, and it is a function of doping.
What will disappear, sir, again?
Huh?
What will disappear?
Sorry?
What will be disappear? The electrons will be disappeared, sir, or what?
Yes, because electron will move this direction, right? But somehow the material has defect. They may be like dopants or something. So it will collide and combine with holes. So it will disappear, like a disease, disappear. Yeah, neutralized, yes. So it may not be able to really go across the interface. So you need to go across the interface to generate electricity. So this is a characteristic length that the electron can go through its lifetime. So if an electron is generated in this region, then we pretty much sure, or we can estimate that there's this amount of electron can go past the interface. Same as holes. If the hole is created or appeared in this region, then we're pretty sure that we can estimate that in this region, the hole in this region will be able to safely go across the interface. So the total electron hole generated by the total electron hole that may be passing the interface should not only account for the depletion width, but also should count for the diffusion length of electron and holes. Right? Any question about that? Because later on, it is related to electron hole generation, because when the light is shining on the p-n junction, it will create the electron and holes as long as the light is absorbed by the band gap. If the light has higher energy than the band gap, it will create a hole at the bottom and the electron at the top. Then in this region, in this Lm plus W plus Lp region, this electron will affected by the electron, and in their lifetime, they will be safely transported to the other side. All right? So when we shine the light on the p-n junction, portions of light that has energy bigger than their band gap will be absorbed. The band gap will be the same everywhere. You see, even though in the transition region, the band gap is the same. We see that it's tilted, but actually it's the same. Band gap is the same always. So when the photon energy is larger than their band gap, they will generate electron hole everywhere, not only in the electron diffusion length area or photon or hole diffusion length area, but also it can be generated in the depletion region as well. So now, under illumination, depletion region has electron and holes again, not only depleting anymore. Okay, so the optical generation will be sent everywhere, including here, including the neutral region. But actually, there's large electron holes, and this electron and hole may not be able to safely pass in the interface. So we neglect the contribution of electron holes from the place far away from the interface. We only consider these three regions. And the generation will be sent everywhere. So the optical generated current will be generation rate, which is per centimeter cube per second. How many electron hole pairs will be generated per second per centimeter cube? So if we times this GOP, optical generation rate, times area, times the length, this will be volume, right? And the times Q will get the current that we are going to be generated by the light illumination. So again, we just rewrite this equation. Now, we want, yes?
I have a doubt, sir. If the diode is a little bit wider, the radius of that diode is
Wider.
wider.
Oh, wider.
Yes.
Then the area will be wider.
Then
Area
current
will be
is
large.
small.
Current is small? No, current will be larger.
Large.
Current will be larger because we are assuming that light is can penetrate the whole materials. So if you have a larger cross section, then basically you can absorb more light. So per more light per total volume. So you can generate current. But actually the current density might be the same though. But if we divide it by cross-section area, then it will be the same. Okay, now we want to combine these two effects. Previous one, this is only diode when biased. Okay? Then this one is only under illumination without bias. What if a diode that is under illumination while it's biased? Then we just need to combine these two equations together. So we end up with this equation. It looks similar, right? From the diode equation, right? Yes. But plus the IOP. However, we put a minus sign here. Why? Because the current direction is different. Let me show you. This one defines the forward bias direction as positive. All right? But IOP generates the current opposite to the current that is forward biased.
That's why it's marked.
Yes, that's why we put the negative sign in front. So eventually we have this kind of equation. Very important. Anyone don't understand this equation?
So at the final it will be added?
Huh?
At the final it will be added because you said it is opposite.
Yes.
IOV it is opposite, so it will be minus?
Yes.
Then minus with minus it comes.
No. Okay. Very important. Then I need to talk about it more. Say, this direction by light illumination, generated by light illumination, is this the same direction as drift current direction? Right?
Yes.
Yes or no?
No.
No? Yes?
Drift.
Drift current, is that the same as drift current? Drift. This is drift. This is when reverse biased. The direction, the electron go to the right, hole go to left. Okay. This is the current generated under light illumination. What is the direction? Electron will go to the right and hole go to the left. So it's the same. So the current by photon generation is the same as drift current. The same direction as drift current. It's opposite to the direction of diffusion current. However, this equation, the first term on the right-hand side of the equal sign, is defining the diffusion direction as the positive. So we need to minus the effect of current that generated by photon electrons. All right? So this is really the minus sign. Not minus and minus become plus. No. It's really minus. So it will decrease. It will down offset the whole current by this IOP. Right? So to complicate this equation, then I will write this to warn you that there may be very serious theory, but actually it's not. It's very easy. Okay. So now we are drawing this diagram. The diagram is biased. When this is only biased, the curve will be something like this, right? Without optical generation of electron. Now, when the PN junction is illuminated, then what will direction of the curve movement, the offset, going down, right? And this curve is a function of the generation, optical generation. So if this light increases, then it will going down more, right? So it's very straightforward. It's going down, really going down, not going up. Sorry? Yes, very similar, even though we are not biasing it. We are not biasing it only by the photo illumination. They will go down and generate electron holes, move the same direction of strip current. So it looks like as if we are biased, reverse bias the diode. So actually, we also call this generation because this, when we are not illuminated, this very small I node, before we also call generation current because that is generation by thermal, those thermal vibration. So it's also called generation rate. But at the room temperature, this is so small we cannot feel that. But by light illumination, this generation will be very significant. Significant enough that we can use that as a solar cell. Okay, so very easy. Now, what will be the wavelength effect for the solar cell? We might need to do the experiment this afternoon. Oh, actually, no, late this morning at 11 o'clock. We might want to test if the red light will be suitable for solar cell or green light or blue light. There might be some differences. Okay, so this is just show you an example. And this is not necessarily the blue, green, red. This is just to show the wavelengths different, the light, photon with different wavelengths. All right? So if this band, for the material, semiconductor material, it has band edge, band gap corresponding to this green light, then will green light be able to activate the semiconductor to generate electron and holes? Yes, it's exactly just enough to excite the electron and leaving a holes. And these electron holes are charged. They can be moved under the influence of the field. Okay? Okay, now if we have another photon with larger energy, that means we have shorter wavelengths, stronger, more powerful photons going in. Then this photon energy will excite the electrons go far above the conduction band edges. All right? Then it will not stay here because there are a lot of orbitals for them to stay. So it usually will drop down to the valence band until they cannot drop further in the conduction band. So they will go down to the edge of the conduction band and release the energies from where it is excited to the conduction band edge through the form of thermal energy. Okay, so it will hit the semiconductor, and heating might not be good thing. So actually, we cannot take advantage of this one because we cannot use this portion. So it's wasted. So if you are using the photon with energy much higher than the band gap of semiconductor, you are wasting your energy. The most energy it has been dissipated by the excitation of electrons in the conduction band. All right? Now, if you are using a photon with weaker energy or longer wavelengths, then it will try to excite the electrons, all right? But this one cannot afford to excite the electron to the conduction band edge. And it may go here, but there has no orbitals for the electrons to stay. So the electron will not stay. It will come back to the valence band without being excited. So that means this small energy, the photon with small energy, will not be absorbed by this semiconductor. So it will pass through the semiconductor without doing any interaction. So from the perspective, the red light is transparent to the material, or the material is transparent to this kind of light. So for example, if we are using a glass, you can see through the glass. That means all the visible light cannot excite the glass, cannot excite the electron in the glass from valence band to conduction band. So, however, the glass can be UV protective. That means the UV light, as long as we wear the glasses, we can protect the eyes from the harmful effect from UV, even though we are wearing glasses without color, right? Actually, color glasses is very dangerous, right? So that means UV may be able to excite the electron and holes and being absorbed by the glasses. But for the visible light, energy is not high enough, so it can safely penetrate through the glasses and be seen by us, by human eyes. Okay.
So, can
Yes?
we increase the energy in that electron, the red one? Can we increase the energy without changing the frequency of that light?
Sure. If you increase the frequency, then it will change its color too.
Yes, but we'll use the red one. We'll not read any frequency. We'll use
The red ones.
By heating that solar panel, the electron will transfer to conduction band.
Oh, if you hit the semiconductor will have thermal effect. So the conduction band will be lower and valence band will higher. That is because the vibration caused by the reduction of band gap. So, but you need to hit the semiconductor very high to feel this effect. If you only hit to 100 degrees, then you hardly have any difference. Okay, so this is so-called absorption coefficient. So this is very interesting because what is absorption coefficient? That is a coefficient to measure the light at certain distance, impinges on material. At certain distance, it will decrease to its 1 over exponential, right? So the higher the absorption coefficient, the higher the absorption efficiency of the material on certain wavelengths, all right? So take a look of gallium arsenide. Gallium arsenide, for wavelengths longer than 0.9, the absorption coefficient is very low, right? That means it is not an efficient material to absorb the photon with wavelengths longer than 0.9 micrometer. Okay? But when the wavelength reduces to less than 0.9 micrometer, the absorption coefficient increases steeply. That means it is an efficient material to absorb the photon with wavelength smaller than 0.9 micrometer. Okay, so what does that mean? That means the gallium arsenide band gap of gallium arsenide is equivalent to the energy, photon energy with wavelengths around 0.8 or 0.9 micrometer. Can you understand? Okay, so different material have different band gap. So
what is that y-axis?
y-axis, absorption coefficient. Absorption coefficient, that means that is a parameter to know how efficient this material can absorb light.
If it's more efficient, if it's more than
It's more means it's more efficient. It can absorb very large amount of light, right? And if that is zero, that means it is transparent to certain of the photon for certain wavelengths. So on the right-hand side, on the left-hand side, the alpha is always increasing. On the right-hand side, the alpha is always decreasing. But there is a step jump for certain material. Different material has different jump wavelengths. That is the place of the wavelength according to the photon energy, the band gap of the photon energy. Right? The photon energy is equivalent to the band gap of semiconductor. Right? So from here, now you will be able to know what's the band gap of those materials. Right? For example, gallium arsenide increases this line standing here, indium phosphide standing here, and the germanium is around here, and this compound material or indium gallium arsenide standing here. So let's just compare these two. So I will ask you a question. Now this is a test. Raise your hands. Okay, again. There's two compound semiconductor. One is gallium arsenide, one is indium phosphide. Which one has a larger band gap? Raise your hand. Don't voice your sound. Because I want you to determine by yourself. Yes? Huh? Sorry? The yellow one. Yellow color has a wider band gap. This is what you think. But I want to ask everybody. So you might be right or wrong. I don't know. At this time, I don't know. I want to know the opinion of the majority. Okay? And see that if that is correct or right. So I will repeat my question. I may need to explain again. Alpha means absorption coefficient. It is a parameter to test if that is efficient material for light absorption for certain wavelengths of light. Right? So usually on the left-hand side, the wavelength of the photon becomes smaller. That means the energy is larger, bigger. All right? And for the right-hand side, it means the wavelength, the photon energy is lower. All right? So what is the edge means? The absorption edge means at this edge, this wavelength, the photon will correspond, is exactly corresponding to its band gap. All right? So we want to compare gallium arsenide and indium phosphide. Which semiconductor has bigger band gap or wider band gap? you know, for this one, it's for gallium arsenide again. For gallium arsenide, for weaker photon, it is transparent to gallium arsenide. So gallium arsenide will not be able to absorb it. It gets passed through. Okay. Until photon is larger than this one, then it will be absorbed. So by gallium arsenide in terms of energy, you know. Okay, so it's gallium arsenide, and this is indium phosphide. Now I'm asking you, which one among gallium arsenide and indium phosphide, which one has bigger band gap in terms of energy? For sure, it's not wavelength.
Yellow.
Yellow. Red? Now, yes?
Yellow one.
Yellow one.
Yellow one.
Because it has a lower energy. Yellow one.
Yellow one.
Yes or no?
Okay, let's do a survey. Do you think, raise your hand if you think the band gap is larger for red one, gallium arsenide. Okay, just a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 12. Okay, put it down. Raise your hand if you think the band gap is bigger for indium phosphide compared with gallium arsenide. Okay, for this one or yellow one. Please raise your hand.
Yes.
Yes. Okay. Okay, put it down. 3 people. Okay. Then I think should be. I think the majority is right. That's why we need to have majority's opinion, because everybody has these shortcomings. Sometimes you don't know, so need to ask someone else for second opinion before you decide to do anything. It's gallium arsenide. Bigger band gap. Yes, because this is indium phosphide. The band gap for this green line is for gallium arsenide, say. So for longer wave, so this for the wavelengths in between the gallium arsenide and indium phosphide, it can be absorbed by indium phosphide, but it cannot be absorbed by gallium arsenide. All right? So say this is like 0.95. For wavelengths of 0.95, the photon with wavelength 0.95 can be absorbed by indium phosphide. So the absorption coefficient is very big. However, the photons with this wavelength still cannot be absorbed by gallium arsenide. So that means gallium arsenide has a wider bandgap. So you need to increase the photon energy with wavelength smaller than 0.95 to be absorbed by gallium arsenide. So the gallium arsenide has a wider band gap. Is that clear enough?
Yes.
Okay. Okay, then just make sure that you understand that. Let's compare this 4-element compound and this 3-element compound. Which one has wider band gap? Is this for the 4-element compound or the 3-element compound?
There is a blue one.
The green one, blue one.
Yeah, blue one, yeah.
Blue one.
Yeah.
Blue one, yeah.
It has
Okay.
wider. It has wider.
Has wider band gap.
No, band gap. No.
Band gap.
I
Band
got
gap.
The wavelength, but just yeah.
Band gap. Okay,
I
let's
misunderstand.
make sure.
I misunderstand.
That's the sign. Okay. Maybe it's a communication problem. I don't blame on you. green one has wider band gap than blue one. So 4-element compound for this certain composition has wider band gap than this one. So wider band gap means shorter wavelengths. Shorter wavelengths. The same as higher energy has shorter wavelengths. Okay? Yes?
Previous slide, please.
Sorry?
Previous slide.
Previous one?
Picture. In our area, there are different places. Every place will take the light from the sun in different frequency. Is it correct? The frequency, the light frequency in Oman, same as in the China,
Light frequency,
that come from the sun.
yes.
In Oman, that same in the China or in America or
Yes,
Antarctica,
yes,
same?
sure, the same. You can tell by the color. If that is red, you know the visible light range, the wavelength of visible light range is from 400 nanometer to 750 nanometer, right? So short one, 400 nanometer, it will be corresponding to purple or violet. The 750 nanometer will correspond to red light. So it's in this range. It's electromagnetic wave. So I'm talking about the wavelength. So if the wavelength is different, then the color will be different. It's everywhere the same. From in Oman and in Taiwan, same. Okay. But again, might be different in different materials because different material has different index reflectivity, right? So the red light in certain, say in glass, has even shorter wavelengths because in reflective index. That's the only place we don't have. That will be changing the wavelengths of the photons. All right, but once it come out from the dielectric material into the air, then the wavelengths will become the same as previous. As long as it's red color, then the wavelengths will be defined. Okay, this is a slide that we showed yesterday. I just want to show you in reverse bias, the majority carrier is blocked by the barrier. So only drift current, those minority carrier will flow past the interface. So this direction will be same as photon electrons. That is the electron and holes generated by the illumination. Okay, so under illumination, we'll repeat this equation. So the curve will downward offset downward instead of going up. All right, so let's define 2 points. This point is, so it's no longer cross-sect this coordinates at original point, at origin. No, not anymore. So it crosses the coordinate system in 2 points. It crosses the voltage axis in a point. We define that as VOC. OC stands for open circuit. That means there's no current. So we kind of shine in the PN junction and without connecting the wires to certain load. So it's open circuit, no current, only voltage. Right? This is an extreme condition. And another point is ISC. SC stands for short circuit. That means I connect this wire together without putting any load. So it's short circuit. So there's no voltage, zero voltage, but a lot of current. All right? So these are two extreme conditions And if we have this equation, it's very easy for us to calculate the VOC. Because VOC is the voltage when the current is 0. So we can put 0 here and rearrange the equation, then we'll be able to get V, where when at that time V is VOC. Okay? And also, we should be able to get the ISC when V is equal to not 0. Okay, so it's even simpler. Okay? So by the equation, we'll be able to quantitatively calculate the VOC and ISC. Okay, but you don't have to worry about at this moment because you don't have this parameter. But actually, this all parameters are recorded, so you can find even Googling. It's very easy. For certain different material have different parameters, but you can always find, at least for convenient use semiconductors. Okay, so this is just a simplification of VOC. Although this equation is very difficult, seems to be horrible. But if you can simplify, you can assume Pn equal, say the doping concentration is similar for each side, and the lifetime for electron holes are similar. Actually, it's about the same order. So, and the generation rate will be this one. It's just a concentration divided by the lifetime. All right. Then neglecting the width, because under reverse bias, it's not under reverse bias. Actually, if you calculate the width that we can calculate is much shorter than the diffusion length. So under the condition of illumination, we can ignore the width without any problem, because usually the lifetime for electron holes, the diffusion length is much wider than the depletion region. So by this case, then by this approximation, we'll be able to get VOC equals KT over Q long GOP over G thermal. G thermal is I know, right? That is a generation rate for I thermal, I0. So basically, you just need to compare this G to the previous G that without being illuminated. Then you will be able to, and take by long, natural log, then you will be able to get VOC. So that means during the time that you increase the G, you will actually increase the VOC little by little, not that significant, because it was taken by long, natural log. So even though it increases, but not increases that much. Okay, so I just rewrite this equation. And is there a limitation of VOC? From this equation, there's a problem about this equation. This equation seems that as GOP increases, then VOC will increase definitely without limitation, right? But actually, there's limitation because of the band gap. Again, I'm talking about, yesterday I talked about the band gap. Because band gap, there's only certain distance that you can have VOC, that saturate. You cannot increase the VOC higher than the barrier between the barrier of energy between two sides, P side and N side. Otherwise, you will create a lot of current that cannot be handled by the semiconductor. So there will be a limitation. The limitation is band gap itself. All right. Okay. But it's no big deal, because what I want to talk about is there's limitation. VOC cannot increase definitely. So this equation only works when illumination rate is not that high. If you use very high generation like the sun, then pretty much your voltage, highest voltage, is the same as the band gap of semiconductor. You can go as high as the band gap semiconductor, but cannot go higher than band gap. So the VOC is open circuit voltage is limited by the semiconductor band gap of semiconductor you choose for the solar cells. All right. This is just show you the limitation. Only this you can play around. If this go above or equal to EC, then it's no resistance. You cannot go further beyond this point. So this is the one limits the voltage of the output of the solar cell or the PN junction. All right? We'll go more detail about that. Okay, so we might break here for maybe 10 minutes. All right? No? Never mind. It's okay, so let's take a break for 15 minutes, then come back. Okay. Okay, so some student approached me saying that we haven't discussed our results of the lab, right? Because we have busy schedule. So I plan to discuss that in the class tomorrow, not today. Because I'm going to show you all the basic. We should be able to end this solar cell stuff by today. So later on we'll talk about at least now you know the wavelength effect, right? We'll talk about the temperature effect. And tomorrow we are going to talk about a new technology called dye-sensitized solar cell. It's not PN junction anymore, so it's something else. So I think probably we finish this part, then we can discuss about the result that you measured from the lab for the previous 2 days, or even for today's lab. All right? And actually, tomorrow morning, if I am informed correct, for the first hour, we will invite an official, also from Taiwan. He will present a 1-hour presentation about the business. How, if you are interested in this business, then what kind of concern you need to face, and what will be, how to operate this business. So it's also very important. So if he comes, then I will be, for the first hour, I will be the audience as well. I was sitting in the audience to you also, and also interested. Yes, I can sit here. Then listen to him. So should be very interesting. Then after that, we will resume our classes and discuss about the result that you measured during the labs. All right? Okay, now we already know the equation. We already know the equation of photodiode. So we will consider the equation by 3 points. Under forward bias, and under reverse bias, and also a third condition that is very similar to forward bias, but it's in reversed current, same directional reverse current, right? So first, for this one is forward biased, so it got very high current, so it's conducting. If you use the battery to bias forward by this PN junction. It forces it to go, the current to go through the PN junction, and hardly any resistance. So it's like short circuit. It's like short circuit. Hardly, you cannot feel the presence of the PN junction. It got short circuit. Fortunately, we have resistance there, so it's not burning down the PN junction. It will be consumed mostly by here. Okay, so it is nothing different than a traditional PN junction. The only difference is this PN junction has been illuminated. That's all. Okay, so in this quadrant, it's just like a PN junction. Okay, conducting PN junction. And now let's go to the third quadrant. Third quadrant, because this curve only goes through 1, 3, 4, right? So let's discuss about the third quadrant. The third quadrant is reversely biased. So this reverse bias forces the current to flow reversely. And with the help of the light, the reverse current no more insignificant. It's very significant now. All right? So, and also, this current will vary with the strength of irradiance, And this curve is very flat. So it is not a function of reverse bias. As long as you reverse bias away, a little bit away from the zero voltage, then you always get a constant current. And this current is a function of irradiance. It's a function of irradiance. And sure, in the negative direction. All right? But actually, negative possibility is defined by human. You can always regard it as a positive, even though we draw here as a negative. So what will be this for? Anybody think about this application? The second one, yes. It is not a function of voltage, but it is only the function of irradiance. The power of solar panel? Sensor, yes. Sensor. You only need to bias this PN junction. Then it can measure the irradiance for you. Sure, you need to calibrate that. But it will not affected by the slight difference or instability of voltage that you apply on the PN junction. It will always give you a correct number without being affected by the voltage. Okay, it's only affected by the power, the irradiance power. So it is a good application in the sensor or photodiode, photosensors. Okay, you can measure the light, right? Okay, so we know this. Now, how about the third possibility, third point? Here, we like forward biasing it, right? Forward biasing it. But current is actually in the negative direction. All right? That means if we put the battery here, forward biasing the PN. Now P is in the positive potential, and the N is in the negative potential. Then we found this current is still reverse in the reverse direction. So is this current driven by this battery or by PN junction? Should be PN junction. This one cannot drive this current in this direction. So that means now PN junction become a battery. and output voltage against this battery and generate electricity. So in this case, we can even remove this battery and still be able to functioning. All right? So now this is look like a battery. Then we can remove this and still be able to operate this to generate electricity. So this is what? Yes, this is solar cell now. So the solar cell, we always operate in fourth quadrant. All right? Okay, so this is just conventional diode for DC-AC conversion. All right? And you may think about this equation because this, I don't know, you may think about this, but this is, for now, it may not be different from the just usual diode. All right? And this is for the photo detector, for detector use. And this for the fourth quadrant. This is used for the solar cell. All right? Okay, so this is what I have talked about. So you can just take a look. Okay, so ignore this example. This example just I want my student to derive this equation, that's all. So no big deal. Okay, this is the procedure of derivation. Okay, so you can buy a textbook and find this equation. All right, so it's not that difficult. Okay, so finally we go to solar cell. So photodiode is not necessarily used for solar cell. It can be photodetectors. All right, but now we are focusing, since this course is for solar cell, now we are focusing on solar cell. So for the solar cell, actually we are operating this in the fourth quadrant. This IV curve in the fourth quadrant. Okay, so you might have idea. Silicon, the VOC is here. VOC is about, actually it's about 0.6. It's not as high as 1 volt. So a little bit, and typically current, this is ISC, is about 100 milliamps in this range, right? About per centimeter square. So this, if you want to be an engineer, then you have to be very sensitive about this number. But so far, it's okay, no big deal. Okay, so this is just a fabrication of a solar cell. Basically, you get a P-type wafer. You got a P-type wafer, silicon wafer, and diffuse some N-type materials on it, so you will form a PN junction. Okay, when the dopant of N-type exceeds the dopant of P-type, it becomes N-type. So it will counterbalance each other, and if you put the dopant, the more heavily doped N over previous doped P, then you will convert that to N-type for the top one. So you need a furnace. You need a furnace and like deposit the dopant on the surface, then heat turn on the heater, turn on the furnace, and let it heat for a certain period of time, say 2 hours. Then some of the dopants or the defect will diffuse into the material. Only need very slight, need very thin layer of P, then we will be able to form PN junction. If you know more detail, you know that the depletion region will occur on the low dope side. So since N dope is very heavy, so they will not develop depletion region that much. The most depletion region will deplete will occur on the P side. So that means you only need to have very thin layer and will you be able to make p-n junction. So it's very easy. You have a wafer and spray that with dopants and putting into the furnace and heat it to maybe 300 and 400 degree and take out, remove the remaining dopants, then you already have p-n junction, right? Then you need to put the metal. For p-type, it's easy. We can be contact from backside. We can make the contact from backside. But for the top side, since we need it to transparent to the light, so we need to have anti-refractive coating, like put glasses and some treatment to reduce the reflection as much as possible, so we can absorb as many as photons available. But this is non-conductive, so we need to put the metal contact before we doing the anti-refractive coating. All right. So you can always see. So if you look this from the top view, look from top view, it will be something like this. This is called the finger structure. This is all metals. This just want to contact the P side. So we have P connection. And N side. And P side is very easy. We just contact from at the bottom. All right? Okay, this okay, so they might have something that beyond the scope of the lecture. So I just ignore this one. If you are interested, you can take a look and discuss with me later on. But because it's a very busy schedule, so.
Can ask the dimension.
Huh?
Dimension. D, how much? Yeah.
D?
Yes.
D?
The width of N type.
N.
N type.
N is very small, like micron. Micron, yes. Okay, so this is a more important idea about how we plot the IV curve. So this is a portion of IV curve that we are interested for our solar cell application, right? So we only take a look of this portion. So the curve will look like this, all right? Okay, and actually it doesn't matter if we define negatives as positive or positive as negative. So we usually flip this diagram over and it will look like this. So if we magnify it, this will be something like this, and with VOC in this location, while we have ISC in this location. All right? Straightforward enough? Any question about that? So this is curve you are measuring for the previous 2 days. So now you are familiar with that, right? So sometimes some people put this as a negative value. You know why? It's because they consider this curve to the diode equation. So that is negative. But it doesn't mind. You can put positive or negative as long as you know this curve is coming from the fourth quadrant of photodiode curve equation. Okay, maybe slightly different because I modified it a little bit. Okay, so again, we have open circuit voltage, we have short circuit current. Then we can operate in any one of the points as long as we adjust the load correctly. We can, this is a characteristic curve for the solar cell. We can operate at any point on this curve as long as you do the matching, the good matching of the load to the solar cell, we can operate. However, which points should we want to operate? We want to operate the solar cell at its maximum power output. So what is the power output of the solar cell? The power output is the current and the voltage multiplication of current and voltage for that point, right? So basically, for the maximum power output is a point that have its rectangular area go to maximum under this curve. Any point that can give you the rectangle area, maximum area of rectangle, will it be the maximum power output, right? So you can just do the math, do the calculation, and find out which one the point. Usually, it will be somewhere a little bit below the flat area, all right? Usually at low voltage, you will have a flat current because at low voltage, you are pretty much like short-circuited already. The short circuit, the band alignment is always flat, almost flat. So you cannot increase the current anymore by doing the bias. So the current is more flat here, all right? So usually the point will be somewhere a little bit lower than ISC, but closer to VOC. That will give you the maximum output. You cannot choose a point with high V. If you choose high V, then it will have low current. So area is not big. You cannot choose low V, high ISC either. If you choose IEC, then V is very low. So it has to, the maximum power, the point for maximum power output should be somewhere at the location when this curve is starting to going down. Okay? So already know VOC, short circuit current ISC, and maximum power is where IV, the multiplication of IV give you the maximum number. All right? We say this point, the current corresponding to this point, we say it's Imax. It's not really maximum current. No, it's just say this point, the point corresponding to this point that gives us maximum power, and voltage that the point gives us maximum power. And we'll define a field factor. Sometimes we abbreviate it as FF. Field factor is the Imax times Vmax divided by VOC and ISC. Okay. We can never achieve this power output. We can never achieve this output because this is curved unless we have points somewhere here. But this is not included in our curve. But still, since we have VOC, so we know our extreme that we may go to VOC. If you carefully design the structure of the PN junction, we might be able to go to VOC. All right? And ISC, even though we cannot find the point at this point, but we know we have maximum current output So there are possibilities that we might be able to have a current as high as ISC. So we put this at the bottom and put this into the top. This is called field factor. That means how good, that is the indication of how good our solar cell is designed.
It will be less than 1, right?
Or always less than 1. Always less than 1. Then we want this field factor as close to 1 as possible. So there's a knowledge about how to construct a solar cell. So this shape is like as much closer to rectangular shape. Oh, they're always doing this design so that we have the field factor very close to 1. Okay, so this is the diagram I just copied from some other source. I forgot from one of the websites. And this is exactly the same as we just talked about. But they use now they invert the coordinate, right? So this is the previous, the blue one or green one. The blue one will be the diode curve. And when you illuminate the diode, the curve goes up, right? So now it's very straightforward. And sometimes we use this symbol to represent the photovoltaic cell or solar cell. It can generate voltage. And if we now define the photocurrent direction as positive direction, we can use this symbol to represent, now we have a voltage. If we put a solar cell, then we have a positive voltage here. If we define this as a positive voltage and positive current, then we have this symbol. Okay, so more frequently we are using even detailed equivalent circuit to describe the solar cell. Since it's a diode, right? So it should consist of a diode, all right? And since it is illuminated, so its behavior is not only a diode, but also a current generator. So usually we will simulate, we will simulate the solar cell as a series connection of PN junction with current generator. This is the equivalent circuit of the solar cell. Always. Okay, so this is current. I forgot to change this to English. Huh? Current generator. Current generator. Oh, okay. Then make sure which side is P. You can find from the diode. This side is P. This side is N. So if we forward bias, it will be conducting. All right. So I just write here. P is this side. N is another side. And current generation is from N to P. Current direction, that's the whole movement direction, is from N to P. Okay? Okay. So this is an equivalent circuit for an ideal solar cell. But you know, nothing is ideal. So it has to have some series resistance and shunt resistance or parallel resistance. We call shunt. Shunt means did not go through directly, but go through the other way. Shunt to get away from it. So this is called the series resistance, shunt resistance, and the series resistance. So for a real solar cell, the equivalent circuit should be something like this. Not only the ideal solar cell parts, but also we connect with shunt resistance as well as series resistance. Okay, so after connecting that, the current finally we applied on the load, voltage and current applied on the load, will be described by this equation. Okay, it's this one is very familiar, right? I know this is diode equation. I know exponential QV over KT minus 1, right? But usually we put it N. N should be close to 1, but sometimes because ofinideality, we put so-called ideality number. That is very close one, but sometimes it varies between 1 and 2. Okay, I don't want to go to that detail, but it's just to simulate the real cases. So this is the diode equation, and this one is current generation by the illumination. Current generated by the light illumination. And this is combination of effect from shunt resistance and series resistance. Okay, so this should be very easy for you, right? Okay, so again, I mentioned about in the previous page that the red one is a curve, the IV curve of solar cell. You just need to find the point we have so that the solar cell have the highest output, power output. And if this area, and what is the field factor? Field factor is the area of the blue rectangle divided by the green rectangle, right?
The field factor, Mr. For what we use it?
For what we use? We want to see if this solar cell is processed or being constructed very good.
So
Because the field, for the field factor very close to 1, then it's a good solar cell. If not, then it's not good cell. But it depends on the material that you used. Not only design, but because some intrinsic property about material that we cannot overcome. So this is field factor is a parameter to tell whether the solar cell is very good, very well processed, or very well designed, or very well chosen. Material has been very well chosen. Okay, the characteristic resistance is the resistance that give you the maximum output. So if you know the circuit, you just put the right resistance so that this is the low line, the resistance line, right? You just need to have right resistance. The slope is the resistance, right? V equals to IR, I times R, right? So R is V over I, yes. So divided by this number, we'll be able to get the resistance. So you just adjust the resistance so that it crosses with the maximum output point of the solar cell current. Then you will be able to get the maximum output, power output of solar cell. Okay, again, this is I took from the website PV Education. So as this has been illuminated then it will go down, right? Okay. So now we try to find the effect of series resistance, shunt resistance on the IV curve. So they are called parasitic resistances. It always comes with solar cells, but we want to estimate. We want to estimate how large the values are, or how small the values are. So this idea about the magnitude of series resistance and shunt resistance, do we want the shunt resistance to be as big as possible or as small as possible? For shunt resistance. Huh? As big? Yes, as big as possible. Otherwise, all the general current will go through this one without going out, without doing the output. So we want our solar cell be made without any leakaging pathways. All right? So it's very important to do the packaging and doing the processing. So we want our shunt resistance as big as possible. Now, how about series resistance? Yes, very good. We want as small as possible. We want the voltage, energy only consumed in the appliances, in the load, in the output load, without consumed inside the circuit, inside its internal circuit. So we want the series resistance as small as possible. Okay, so you may go to this website and try to manipulate the series resistance and the shunt resistance. Okay, for the blue curve, it is ideal, or close to ideal. Close to ideal. That means this is very low. Very high shunt resistance, and this one, the slope of here, is very low series resistance. Okay, I will show you why. But the red one is the parameter I set for series resistance and shunt resistance. When shunt resistance reduces, this line is no longer flat. It will decrease. They will have slope here. That means the shunt resistance is reduced. Do you have the idea about this one for slope? No. Yeah? Who has the idea about to find the shunt resistance from the slope? Who already have this knowledge? Please raise your hand. You? Put it down. Oh, so, okay, thank you very much. So probably most of you still don't have this knowledge. Then, okay, I prepared the slides, no problem. So actually, we can tell the shunt resistance and series resistance from the IV curve. Or, in other words, shunt resistance and series resistance will affect the IV curve. So it will affect the field factor, right? So field factor is a parameter to see if we remove those effect of parasitic series, the resistance, right? So I can also answer the question that one student asked previously. Field factor is also a parameter to see if we have carefully doing the process for the solar cell. Okay, so this is not good. If the slope going down like this means shunt resistance, and this means series resistance. Series resistance, this should be very standing up, and this should be very flat. then we will get a very high field factor. Okay? Why? Because next page, I already write down the equation for you. So you can, this is an approximation. Okay, we now consider series resistance. Series resistance is the slope that we found near VOC. VOC is here, near here, the slope. We can find the series resistance from the slope near VOC. Why? Because near VOC, diode is turned on. Diode is turned on because it's activated, VOC activated, and it's conducting. And IL is constant because current is constant, right? So the resistance of diode, since it's being activated, so its resistance of diode is very small. So the parallel combination of the resistance of the diode and shunt resistance will be even smaller than the smaller one. All right? So it's very close to, since this is much smaller than shunt resistance, usually shunt resistance, unless you did a very bad work about the solar cell processing. Otherwise, shunt resistance will be always much larger than the resistance of the diode. All right, so you should have a resistance, since this is already turned on, so the resistance should be very low. The resistance will be about the resistance of the diode. Okay, so we can control this relationship by like this. We can remove because there's no resistance here at all. So we can remove the effect of shunt resistance. All right? So we only need to concern about actually very small. Okay? And we have this relationship. The current flowing through the diode plus the current flowing through the series resistance will equal to, because this is a current generator, so generator distributed two ways, either flowing this way or flowing the other way, all right, to be the output current. All right, so I diode plus IS will equal to IL, and in terms of voltage, Ri in this circuit, resistance of diode times the current flowing through the diode will be equal to voltage, output voltage, plus the voltage drop that occurs on the resistor. So using this equation, we will be able to get the dV by dIs. IS is actually I, the output current. So this will be, we just put this V. We can get the V from this equation and put this and do the derivation. So we'll be able to get that. And since IL minus IS, derivative IL will be constant, so this will be, derivative will be 0 minus 1. So it will be R diode minus RS. And since R diode is much smaller than RS, then it will be almost equal to series resistance. All right, so there's some derivative about equation. So we'll be able to know dVdi here, dVdi near open circuit voltage. That will be almost approximately, not exactly, approximately equal to shear resistance. Oh, not shear resistance, sorry, series resistance. Now, similarly, we will be able to tell the shunt resistance by the slope very close to the ISC, short circuit current. We'll be able to tell the shunt resistance from the slope of the IV curve very near to ISC, short circuit current. That is the slope here. Shunt, this is to find out the shunt resistance. Again, we take a look of the diagram. Now, since the current is 0, since the current now at ISC, the current is 0. So there will not be current flowing outward to drive the load. All right? So since there's no current, the diode is not activated. So the resistance, there will no flowing. There will no current flowing through the diode. So you can remove the diode. There's no effect of diode at all because it's 0. No current going through the diode. So you can reduce the circuit to this one. So what will be the current, the photocurrent going through? Either going through this way and not going through this way because it's not going to be a current go outside. So we have, but still, shunt resistance plus current resistance will be equal to IL. And actually, okay, and this is the voltage relationship. So we'll be able to get the voltage expressed as both resistance. All right? So if we derive the voltage by current at this condition is the condition at very close to ISC, then we will be able to get this one. And since ISH derived by ISH is -1, it's -1, this is -1, so we'll be able to get this one. And since shunt resistance is much bigger than resistance, usually, unless you did a very terrible job on producing the solar cell, otherwise it will always hold, right? So it will be very close to shunt resistance. All right? So now we know how to observe the effect of shunt resistance and shear resistance from the slope near the VOC and as well as near VOC as well as JSC. But again, you need to keep in mind this is an approximation. You cannot apply this idea to a solar cell that is made by students in elementary school because they might have very bad processing. So this is an approximate equation. This is not exact. But you know, usually as engineering, you need to know if this is a good solar cell or not from the first perspective, at the immediate, the first time. Immediately. So you can look at the curvature to see if this is a good solar cell. All right. So you want to keep the curve near ISC as flat as possible. Usually this can be achieved. All right. And you want to keep this curve at VOC as straight as possible. But even though for best solar cell, it will not be straight. It will always be a little bit inclined, right? That means you always have a series resistance, right? Okay, so this slope give inverse of this slope gives R at IC. This is related to shunt resistance. And the inverse of this slope gives us a series resistance at VOC. Okay? Okay. We are pretty much done for, not yet. We are pretty much done for the curve, the solar cell portion for the photodiodes. Yes, but we still have about 10 minutes remaining. So I will give you a brief idea about the temperature effect. All right? So I will mention about that tomorrow. But since you are going to do, actually you did that already on the first day, because when we put the solar panel directly under the sun, it becomes very hot, right? And the heat even transfer through the electrical wires to the dial, potentiometer. And we can hardly touch the dial because of the heat. Okay? So then the curvature is different than when we measure this IV curve at low temperature. So we don't know. We'll review the curve that you measure on the first day and second day also today. But I just want to let you know, by now we'll be able to tell the effect of temperature. We need to have background knowledge before we can go to the effect of temperature. Okay, so for electrical conduction, semiconductor behave different from metals under the influence of temperature. For metal, it's already a good conducting material. So as temperature increases, the temperature, what will the effect for temperature increase? It will increase the vibration, the phonon vibration, atomic vibration. So it will interfere the carrier transport through the conductor. So if you hit the metals, the conduction will increase or decrease?
Increase. I mean heat, it will increase.
For metallic material. For metallic material.
Yeah, it will increase the conductivity.
For metal.
Yeah.
Metal is already a very good conducting material.
Yeah.
So when the phonon is vibrating, the atom is vibrating because of the thermal energy. It will interfere with electron passing through.
Okay.
So
it will resist that?
yeah, resistance increases. So the conduction decreases. This is for conductor, metallic conductor. But it's different for semiconductors. Semiconductor, although we have this kind of effect, the phonon will interfere with carriers transport. However, there's another effect. Another effect is when temperature increases, you have increased carrier concentration. So this counteract each other, and the concentration prevails a little bit, not very significant. It hardly changes the conduction, but it almost counteracts each other. So semiconductor is not affected by temperature that much in the conduction as the same as metals. It even increases a little bit when temperature increases, but not significant. Okay, so again, this is the profile of the concentration, carrier concentration as a function of temperature. So we already know, right? Okay, so now it's easy, very easy. All right. So this is a typical curve affected by IV curve affected by the temperature. The blue line, now you already know the characteristic IV curve of the photodiode or solar cell. So this is a typical curve for solar cell measured at low temperature. Okay? And the red one is the characteristic IV curve measured at high temperature. As you can see, the solar cell is made of semiconductor. So current increases or decreases? Increases. A little bit, yes. You probably may not be able to see this increase from your measurement because there's always uncertainties or limited by equation. You may not be able to see the difference. All right, I don't know. We'll review the data, measure data tomorrow. However, you'll be able to see the voltage decreases because for the band gap, you have thermal vibration. So it pretty much reduces the band gap of your semiconductor. So the VOC decreases, even though it's still not that many compared with the voltage that the semiconductor have. But it's more significant changes than the current part. So in terms of field factor, which one is good?
The
Blue one. That means you need to have solar cell at low temperature as possible.
Yeah.
Well, it depends to the location, what do you fix?
Oh yeah. You mean the deployment of solar cell panel, right? Right. Yes.
High, that means the other one is suitable.
Sorry?
But if it is high temperature, area what you fix.
Yes. If the temperature cannot be a chosen parameter, then we would have no solution about that. Then we have to always need to rely on this red one. But I just said if we can manipulate the temperature, then it's better for us to choose at low temperature, right? So sometimes we need to use coolant, if possible, to cool the solar cell, so the efficiency will be higher. But again, you need to consider about the cooling system will cost more or less than the extra energy generated. Oh, sure, yes. That you need to always keep in mind the cost effect. Okay, so this is just give you an idea about how to calculate the effect of temperature on VOC. But this is a cumbersome equation. For example, this one I showed you maybe yesterday or the day before. And for each side, this is called respective to P side, and this is corresponding to for N side. Oh, sorry, maybe just opposite, but just corresponding to each side. So the current will be the function of everything. However, intrinsic concentration will dominate because it varies exponentially, right? So once we know this, and this I gave you the equation already, right? Even though I gave you in this form, but ni squared, you can do the calculation and all arrangement and get this situation. So you have to believe me, ni squared can be represented as this. So you can see what is the term that's related to temperature. This one, right? And this one, right? So it only keeps the temperature terms and take the rest of things as a constant, as not related, is independent of temperature. But actually, this is also approximation. Still, every parameter except this k and h are temperature functions. It's not that sensitive as these two terms. All right? So, but for engineering purpose, we don't need exact, as long as we can control the system precise enough below the requirement the error, then we will be a successful engineer. All right? So we can plug this I and I into the previous equation and get this equation. This equation will be the I0 current as a function of temperature, where gamma will be close to 3. And if you are engineering, usually you'll say, oh, this is close to 3, but not exactly 3, to account for the temperature dependence of other parameters. Very insensitive dependence of other parameters than this one. So by this one, there's a VOC. VOC is the equation. Now you already know, right? I gave you just this morning. So you just plug the I0 into this, we'll be able to get VOC. So VOC will be like this term. And if we derive this by T, it will be like gradient, the coefficient dependence on temperature coefficient. So we'll be able to get that. So this VOC will change with T with a coefficient of 2.2 millivolts per degree. And minus. That means if we increase the temperature, the VOC will decrease accordingly. So it's not good. We want to VOC as good as possible. I just want to show you, we are doing this with basic theory. It's not just measurement. We have the equation to describe. That's why I need to spend 2 days or even 3 days going through the detail that give you the basic equations. And we can do the current, the effect of temperature on current as well by using equations. So we'll be able to get 0.0006 positive per degree. So temperature has also effect on ISC, but it's not that sensitive, or very insensitive. Maybe still stay at the same current, but if you are very strict, then it will increase. Okay? But this increase in current cannot afford the decrease on VOC. So still, even though ISC increasing in temperature, we still need to choose low temperature to have high output of the solar cell. And field factor as well, we can find the temperature effect on field factor is decreasing because basically because of decreasing VOC. And the power is also decreasing because of majorly by the decrease on voltage. So this will be the negative value. Okay. And we pretty much talk about the wavelength effect of solar cell module. we talk about this one. For light with long wavelengths is now solved. It can not activate the electron excitation, so it's transparent. All right. So green light may be good enough, exactly good for the excitation of electron-hole pairs. However, if you choose energy, photon energy, too large, too much bigger than the band gap, then there will be a significant portion that is reducing so-called cooling or the excitation. Then you are not going to use portions of utilize the energy of the photon with larger energy. So for certain semiconductor, you need to have a certain photon with certain wavelengths. Okay, for solar cell, we cannot control the incident light because sun already has solar spectrum. And naturally, all the plants that want to use a solar cell already know that the major wavelength is in what color? In green color. That's why most of the plants are in green. Because in green, they will absorb most efficiently absorb the solar light, right? Okay, so we need to carefully. So since we cannot choose the incident light from the sun, then how to maximize the solar cell efficiency? We choose a semiconductor material that best fits the green light or best fits the solar cell spectrum, right? But still, we cannot use everything because once we choose the band gap of semiconductor, there will be the photons in the solar cell spectrum not absorbed by this semiconductor, like infrared or red light. If you have band gap that is suitable for green light absorption, then it will not absorb in red light. So red light is passing through without being absorbed by your semiconductor solar cell. So it is wasted. And also, even though you choose a band gap corresponding to the green light, you cannot fully utilize the energy of blue light. Even though blue light can give you the electron-hole pair, but their energy are partially consumed in the cooling procedure. It can generate heat on the solar cell and being dissipated by the conduction convection or something else. It wasted and cause global warming. It's very hot, become very hot. So they're always lost. So it is very difficult to choose the best wavelength. Even though we choose wavelength, we still cannot utilize the whole spectrum of the solar cell. So this is pretty much the typical spectrum of solar cell in terms of wavelengths. All right? So it is from UV. UV is a wavelength below 400, shorter than 400 nanometer. And the visible region is from 400 to 750. So I just draw the color here. And you see a lot of photons in the IR, infrared region, that we cannot use. It's a waste. There's still energy. And you see, most of the energy, actually solar cell is here. Even though the peak is somewhere near the green one, but there's still energy here. If we just choose one band gap, then we are still only to use somewhere near the band gap of the visible light. We are not using this infrared as well as not using the ultraviolet. Okay, so this diagram is spectral irradiance as a function of wavelength. Can we convert this diagram to be as a function of photon energy? E equal to h mu. Mu equals to what? Equals V over lambda over V over C. C is like, huh? Yeah. Yes, C over lambda. C over lambda. C is light speed or light velocity of light. So it's very easy to convert between these two coordinates, these two variables. So we'll be able to convert this diagram to this diagram without problem. All right? So, and extraterrestrial and terrestrial, because our atmosphere absorbs some portions of solar light. So it is different from outer space and on the ground of the Earth. Okay. So if we integrate this photon flux, this number of photons, we'll be able to get this one. Right? We need to integrate the photon numbers from here. We'll be able to integrate total numbers of photons in the solar cell that irradiate on the Earth per centimeter squared, per unit area, per second, per time. So this is the number of photons that we receive, regardless of infrared or UV or visible light. This is as many as possible photons that we can absorb, we can receive per unit area, per unit time. It is around 10 to the 21s per meter square per second. So you see from zero, because energy can be very high and zero. So if you integrate from high energy photons to low energy photons, there will be this value, 4.0 times this one. These are many photons, so many photons that can be received by us. Okay, so how to choose the band gap to utilize this spectra? If we have this band gap, we choose the band gap of this value, then the photon energy higher than the band gap will be absorbed and generate electron and holes. All right? So this is the area that we can use for our solar cell power generation. However, for photon energy larger than the band gap, this portion is wasted by heat dissipation or cooling process. Can you understand? Okay. Now, for this portion, we cannot use this because for this light, for this photon have less energy than the band gap of semiconductor that we chosen for the solar cell. So this photon got passed through the solar cell without being absorbed. So the energy in this area cannot be used by the solar cell either. So for generating maximum power, to utilizing the solar spectrum, we need to consider the full spectrum. We need to have this integration curve, then find the point along this integration line that give you the largest area of the rectangle. Right? Okay? So very simple. Maybe too late for today, so I'm a little bit hurry about this lecture. But you can take a look, and I will give you the files tomorrow. And take a look. You will be able to see it's very straightforward. It's not that difficult. All right? So you need to choose the best band gap. What will be the value for solar spectrum? It is about 1.1 eV. So you need to choose a band gap of semiconductor around 1.1 eV. That gives you the best solar light collection efficiency for the power generation. So you cannot choose any semiconductor. You can only choose semiconductor with band gap very near to 1.1. All right? So this will be the maximum efficiency that can be collected by semiconductor. Usually the highest efficiency will be close to 1.2. All right? So I will correct it. It should be 1.2. But you know, silicon band gap is about 1.1. It's very close to 1.2, so it might be okay. But this is the current technology that used for collecting solar spectrum, but it's never close to the ideal situation, you see, because there's always shunt resistance and series resistance and another defect. So this is the upper limit of efficiency that we can get by our semiconductor. There's still something that we cannot control, all right? And as an engineering, we just want to try to bring this dot, this point, as closer to the limitation as possible. That's our work, okay? So today, it might relate to our work today because we'll try to find a semiconductor solar cell with different material, made of different type of semiconductor, and it will give you a slightly different output of the energy output, and you will tell, you'll see in this afternoon, all right? Okay, so I will conclude my today's lecture. Is there any question, any problem regarding to today's lecture? No? Okay, sorry for that. Sorry for that. But today's lab is very experiment. The first one experiment. We put the light source as a in the fixed position, but tilting the panel towards the source. So if we standing, we put the panel standing up, then it should receive the highest maximum irradiation, right? Okay? And we will gradually tilt it from 90 degree gradually to 0. And at 0, you should expect the efficiency is the lowest. Although it's not 0, because you still have scatter light from the room, and our simulated light source is not like a sun. The sun is like a point source, but we have very big source, the light source. So there'll always be the scatter light that cause some power output of your solar cell, the solar cell that we are in experiment. But qualitatively, we want you to know the effective angle, okay? Now, so we need to measure the result every 10 degree. So from 90 degree to 0 degree, we have 10 data. So are we going to measure the 10 IV curves? No, because we already practiced the measurement IV curve before. We are going to measure the voltage only. And voltage, from the voltage, variation of voltage, we'll be able to know the strength, the power output. Because today, I already told you the curve, the IV curve of solar cell will be something like flat and going down, right? So as the irradiance increases or the absorption increases, this curve will moving upward. So it will change the voltage, right? While the curve moving up, it will increase the VOC as well, right? Even though the difference is not that much, but it still changes the voltage. So today, we are not going to measure the IV curve anymore. We just measure the voltage. So it's very quick, just measure voltage. Then we will be able to tell the voltage difference as a function of angle. Very easy. This is the first experiment. And for the second experiment, it's even easier. We still measure the voltage, but use different light source. We use LED light with red color, or green color, or blue color. We just need to record 3 data. But again, we have 3 kinds of solar cells. We have 3 kinds of solar cells. So you need to measure all 3 kinds of solar cells with different 3 type of the LED light. So you have 9 data. All right? Okay. So for the first experiment, for the angle, we also have 3 kinds of solar cell. So not only you measure 10 data for 1 solar cell, you actually need to collect 30 data for the first experiment. All right? We have 3 kinds of solar cells. 2 among these 3 are solar cell, actually module. The solar cell, 4 solar cells series connected. So after you measure the voltage, you should divide it by 4 to get the voltage for each cell. All right? For the third solar cell, you will see a larger one, longer one with a flexible property. That one is series connected by 12 solar cells. So the voltage you got from that special solar cell should divide it by 12. The rest of another 2 solar cells only divided 4. But there's a medium one. You can tell the 12 connected in series. That should divide it by 12. All right? Okay, so teaching assistant will show you more detail. If you still didn't understand very clearly, I'm very comfortable with that. That's normal, but you will be able to know the detail during your experiment. All right? Okay, so now are we going to use a group that we have for yesterday?
Yes.
Which one will be the first one? Now starting from... Okay.
Okay.
Okay, so you take over.
Okay, I want to talk about
Okay, sure. Yes.
Okay, this is the 90 degree. And now 80 degree. $70. 60. 50. 40. 30.
بعد واحدة زود
أعطيني الفريم ريت. هذا تشوفون 1 2 3 4 5 6 7 إلى 8 عندهم مابا 80 degree. 70 degree. 60 degree. 30.